Yeah, it's here. Yeah, so welcome on the DataOps meetup, David. Stage is yours. Welcome. Yeah, we don't hear you. Yeah, sorry, David, we don't hear you.
Sorry, one sec. Can you hear me now?
Yeah, now it's much more better, but the presentation, yeah.
Sorry, the went ahead on me. So thank you very much for the invitation. My name is David Karamgard. I'm a principal software engineer at Splunk. Previously, I worked for a company called Streamlio that was acquired by Splunk. So that's kind of why there's two different titles on the slides. But thank you very much for inviting me, and I look forward to this, telling you a bit about Apache Pulsar, which we consider the next generation messaging and queuing system. So a little bit about me, so you know who's behind the voice here. I'm, again, a principal software engineer at Splunk. I'm currently writing Pulsar in Action, as well as previously co-authored Practical Hive. And I'm contributor to Apache Pulsar and Apache NiFi projects. And out of those two people, hopefully you can pick out which one's me and which one's Steve Wozniak. So you know what I look like. But let's get started. So today we're living in a connected world. Data's coming from multiple different sources, multiple different places. We need a solution that will help us ingest that data, process that data, analyze the data, and make business decisions, functional decisions around that flow of information. A lot of these, and again, there's just a ubiquity of real-time data streams and events that comes in from multiple different sources, and everything from IoT and streaming devices, connected car, mobile devices, location information, real-time chats, etc. There's just tons of data sources, upwards of 40 some petabytes of data generated per annum, and that's just growing exponentially and continuing to do so. So we need a way to process this data and handle it, right? So let's just talk in general concepts around what event and data stream processing is. So in general, you have events that are analyzed and processed as they arrive. You don't wait until it's batched, landed into a data system, and then do analysis on it. You want to react to the data as it comes in. That makes the decisions timely, contextual, and based on fresh data, right? There's some business value about making a decision upon data as it's in real time. So think of the use case where you have a connected car, you're having an autonomous car. Obviously, you want to detect that item in front of you and brake right then. You don't want to look at it after the fact and after you've already crashed your vehicle into the car in front of you. You want to react in real time. Obviously, decision latency is what I'm talking about there, and that becomes eliminated. And you're talking about data in motion. Data doesn't really have to be stored anywhere to analyze and structured. You just sort of react to it as it comes in. Some of the different processing patterns that are starting to emerge in the field, obviously it's an emerging field and continuing to grow, but some of the ones we've seen and continue to see are monitoring. So that's like real-time monitoring of things like your streaming systems, IoT systems, industrial IoT, things of that nature. Obviously very useful for microservices as well.
Yeah, sorry, David, can you unmute
Yep,
yourself?
no worries. Yep. Another use case we're seeing is microservices. So the traditional use microservices pattern is around REST-based, and you have point-to-point, gRPC sort of messaging, but that's obviously stateless and not persistent. So if something happens, if a microservice dies while it's doing the analytics, you'll lose that information that was passed. So a messaging system in between is something that's very useful as well. Your traditional workflow type of use cases where you're doing sort of like a structured event comes in, an order comes in, you want to walk it through a certain process through order fulfillment is another good use case for event-driven patterns. Models, machine learning deployment of models and inference being deployed on the edge is another one, and the real-time IoT analytics and things of that nature are also good use cases for event streaming. So in general, the stream processing pattern sort of looks like this from a performance perspective, right? You have a messaging system, the data comes in, it first gets written to storage, and then you have to pull it back out and do into a data processing or computing layer. You do the processing on there again, you create an additional secondary result based on the incoming data, and you write that data back in, and you repeat the process over and over again as you do the process. That's sort of your typical pattern so that you never lose the data. It's not done in memory. And then there's on the side of the storage, there's a direct access to data serving layer. So if you want to query the data directly using SQL or some other terms, we also support that with Apache Pulsar, so that you don't have to write, and you can just run an analytical query like you're, and do some analysis on the data as it sits in this local storage area. So what is Apache Pulsar? Why we think it's different? It's really, if you take a flexible messaging system, a queuing system, and it's backed by a durable log storage. And we'll cover all the different architecture, what that means and what that gives you, and why we think this is better to some of the existing messaging systems out there on the market, which always comes up, and we'll make those comparisons as we move along. So what are some of the key concepts around Apache Pulsar? I'll introduce these terms, and so when I talk about them later, hopefully it gives you some point of reference. But from a logical standpoint, you partition off Apache Pulsar cluster into the concept of tenants, which represents individual groups or organizations within a larger, sub-organizations within a larger organization. In this case, a marketing team, a sales team, a security team, that sort of team, analytics team, would all have their, would constitute a tenant. And then you can implement security at that level to prevent access to your data structures underneath. All of your data would belong to that tenant, and only your people within that group should be able to access that data, which gives you some security and privacy around the data. In between is a concept, and then on the other end are topics, right, which is your traditional topics, data, FIFO queues, data comes in, data comes out, you publish the data there, people subscribe, consumers come in and read the data off of those topics. But in between the tenants and topics is this logical construct called namespaces. And what those allow you to do is to group topics together that have, for administrative purposes, that you want to do, set certain policies on. For example, data retention. How long do I want to keep the data in this particular topic or these topics? For example, sometimes I want to keep it for 10 minutes or 24 hours. Others you may want to retain forever. And then additionally, you can set things like security policies, like who can come in and access these things, et cetera. So it's a nice logical construct that allows you to further filter data access and retention and replication and things of that nature. All can be controlled with the concept of namespaces. Obviously, topics, as I mentioned earlier, is your basic data in, data out, lowest level construct within logical construct within Pulsar. Producers write to topics, consumers read from topics. Messages get stored there, and over time, consumers read those, acknowledge the messages. Once all the messages have been acknowledged, again, depending on the retention policy, then they can either be deleted because it's been delivered to all expected consumers, or it can be left around for future consumers based on the retention policy, again, you want to set for those particular messages. But they all live within topics. And then lastly, there's a concept of topic partitions. You can have multiple partitions within a topic. Now, unlike other messaging systems that use partitioning, and we'll cover this in a little bit later on, that use partitioning as their primary to scale out their topics to overcome some of the limitations in their system. This partitions here allow you to scale out the serving layer only within Pulsar. So they're meant to scale out the number of topics, but really underneath the covers are implemented individual topics and just have a logical construct as well, which you can have multiple producers and consumers on topic partitions as well. So if that's part of your traditional design, we also support topic partitions within Pulsar. Another concept when it comes to storage is the concept of segments. So I mentioned earlier we're durable log storage, right? Or write-ahead only sort of log storage. Within that, we have the concept of partitions, which we'll dig into a little bit later on but basically, rather than have a single continuous logical structure on disk from start to end, we prefer, and that constitutes your entire topic, prefer to segment out or partition the storage of that data of that topic into different segments, and those segments can then be replicated across storage layers so that you have your replication is done there. It's at a much smaller, more granular level than a partition replication in a messaging system such as Kafka, for example, where the entire partition or entire topic is stored on a single logical disk sequence from beginning to end. So let's talk a little bit about the physical architecture now that we've covered some of the logical architecture points. This is Apache Pulsar, consists of a separated broker layer, a serving layer that has all these independently stateless brokers that can serve any sort of requests, and then a separated against tiered storage layer that allows you to independently add books, and they can be, each one can be scaled up independently from the other one. So as you load, if you're in a DevOps sort of situation and you can detect and auto react to these sort of events, if your broker layer becomes slow, you can scale up brokers to offload some of the work. And similarly, if your storage becomes too full, you can just add additional bookie layers, and that's where all the storage takes place. So let's dig in a little bit about what those brokers are. It's the only point of interaction for clients. People actually, you're exposed to those brokers, you're given a client, and you serve all the different messages, and the consumers likewise have the same thing. So brokers acquire ownership of a group of topics, and then they serve them, which is great. So again, if you have a consumer writing to the same topic in that broker, and you have the publisher on the other also going to the same broker, that allows us to, in some cases, serve that data directly from cache on the memory without ever having to go to the broker layer at all. So it becomes much quicker to serve, data in that particular case. But that is not a requirement. So the third bullet point is that the broker doesn't really have any durable state. So it doesn't really depend on the data being in there. If the data is not in the cache and we don't have to serve it, we'll go to the independent bookie layer to get that information and return it to the consumer who's looking for the data. This also provides a service discovery mechanisms, right? So the client does not have to, so it will automatically find the correct broker for that particular topic for the client. So the client comes and says, I'm interested in topic A. This discovery mechanism figures out that's broker number 3 in the cluster and hands that off to that particular broker, and the serving is handled automatically. The client doesn't have to hard code any sort of information or load balancer around which broker wants to go to. He automatically discovers it. And if it ever fails over and recovers it, the same thing happens automatically. And so this is how it looks like more of a visualization thing. So again, you have an Apache Pulsar topic, multiple brokers in there, in this case 4, multiple producers, and then consumer groups. So you can see in this case, for example, broker 1 is serving topic 1, partition 1, and producer 1 is writing to that. And then there's a consumer group, consumer A1, that's reading from it in the lower left. And there's also consumer B1 that's also handling that information. All that meshing and wiring together is handled automatically through the service discovery. And if any one of those go down, they'll automatically fail over, and another broker will take over for broker 1. It's not really any sort of latency or any sort of issues related to that. The key that we think is one of the differentiators to our messaging system is consistency. So a lot of messaging systems, when you publish a message to the broker, they will write it to the lead topic or one partition and then acknowledge back that they've received it. And then there's a background mechanism that goes back and fills in and replicates that data back to these standby brokers or storage locations. We don't do that in Pulsar. Pulsar, you can see those dark outbound errors indicate that we write the data to all 3 bookies that are selected simultaneously, and we'll await the acknowledgement back from those bookies, all 3 of them, or at least the number of quorum, the required quorum, which is configurable, that we have 3 acknowledges, and then we tell the producer we've received the message. So we eliminate or reduce the possibility of data loss in this scenario. Additionally, once within that process itself, so we do the sync, the bookies not only just get the data and keep it in their buffer cache of memory, it's forced and F-synced to disk. So there's no way that there's a potential for data loss in other messaging systems if they acknowledge and the messages is only within your broker memory. In this case, we actually force the data to disk every single time, and that way we ensure that there's no data loss. We can accomplish this because we have isolated read and write paths within the bookie itself. So the writes come in and they get F-synced to the journal and put into a ledger storage, and then the reads come directly off of the ledger storage itself. So the journal you can actually separate those on separate disks, at least for the journal, for the incoming writes, which allows the performance of Pulsar to be much faster than other messaging systems which use it all on the same device. We alleviate the bottleneck at that particular hardware layer. Obviously, you can drill more information on this on our website, but this at a high level is basically the secret sauce that allows us to perform better. So let's talk a little bit about about the segment storage and how we store data logically, right? So there's, within Pulsar, you'd have a topic over time linear there with that on top. Now, obviously, rather than store that potentially, if you wanted to store that in another messaging system such as Kafka, you try to store that all on one continuous disk segment on one physical disk on your broker storage. Obviously, that doesn't scale. That basically becomes limited to the maximum size of your disk partition. So the solution instead was to basically take that topic and create a logical construct on top called segments. And by default, they're like 50,000 entries within a topic becomes an individual segment. Once that segment is written, it can become sealed, and then it is also replicated simultaneously across three separate bookies, or three separate bookies down here at the bottom. So segment number one can be stored in the first one, and then the third one, and then the fourth one as you can see fit. The second segment, etc. Once that segment's closed, you open another one, keep it pending the messages, but you spray the data out across multiple disks. That way, not only do you have redundant copies, but you also have the ability when you come back in to read it, that the bandwidth is also, you can access multiple disk drives and have that scalability come back out when you read the data back out. This also then supports the resiliency factor that I talked about. So these, if any one of these bookies actually die and you were particularly reading off of, you still have two other copies within the system of the data, so you're safe and you can continue to serve those messages for those, or request for those older messages. So for example, in this case, if this particular bookie just dies, you can see that segments, 1, 2, 3, and 4 that it currently has stored, there are still multiple, there's two copies of every one of those segments still out there across the bookies. And they'll just immediately fail over to other systems, and they will continue to get replicated, and the brokers will continue to go and read the data off those bookies that have the active copies of those segments. This also allows for seamless cluster expansion. So in other messaging systems, such as Kafka, you'll come in and you're limited to the number of disks. So if you wanted to add an additional node to a Kafka cluster, then what you have to do is not only add that node to the cluster, but then you have to basically repartition that particular topic and say, okay, I used to have three partitions, now I need to have 4. And that becomes basically a stop the world scenario, as all the data that was in the existing 3 partitions gets recalculated and hashed and spread across the four nodes now. If you have the 4 partitions, now it has to get stopped and spread across. Once that is done, then you can resume processing. But that's a very painful process, as anybody who's had to do it before, including myself, can attest. It's kind of a very bad scenario. In our scenario, since within Pulsar, you have a decoupled layer, you can simply just add an additional bookie to the bottom layer if they all become full. Just slide one in, and it automatically becomes it registers itself, and it's eligible to take new segments. So it doesn't matter where those segments are, where it comes in, it can just immediately come online and start serving requests immediately. There's no additional shuffling of the data required, because that is done at the segment level. Additionally, since we've decoupled the storage, it allows you to also offload some of your data, your longer term stuff, to low-cost storage such as S3 or Google, Object Store, NAS, or similar things, and I've written some of that code to help do that. But basically, that allows you to keep your data indefinitely. Other messaging systems will claim that yes, you can have infinite data retention, but if you look under the covers, you have to serve the layer, your broker has to be co-located with the data in order to recover data from a low cost storage solution such as S3. Requires you in those types of systems to not only spin up that broker, but then have a process that loads the data back into those systems as well. Once all that process is done, then you can actually begin processing the data again. With our solution, you don't even need an additional bookie or broker. You can simply read the data directly off of that S3 storage, because it's just a pointer. So within Pulsar, the bookies connect over a network to the brokers, connect to the bookies over a network connection. There's no different between that and connecting to an S3 reader. We just connect over to that data and read the data directly. There's no additional hardware cost to do this. So it's a nice solution, allows you to really truly have infinite data retention within your messaging system, which is useful if you're going to use it for event sourcing, or use it as your true message system of record, for example, solution for messaging systems. So I alluded to it earlier. Let's just sort of look at this visually, what we're talking about, right? So you have a logical partition on top with multiple segments across each one of those. The brokers will serve those different segments from the warm storage layer. They will have their cache where the data's been written in and also persisted to disk, but you can serve the messages off of there directly. If not, then the data is also f-synced to the disks here at this layer within physical hardware on your cluster. If you have a EC2 instance in AWS, for example, those are collated on the bookies there on SSDs backed devices. Additionally, if that data becomes too loud or too long, set of retention policies, for example, every 24 hours offload it, it gets pushed to a third storage layer on S3. And historical reads can be still served off of that. So the broker, if the client comes in and talks to the broker, it'll first try to look into warm storage to get off the cache. If there's a cache miss, it'll go to the bookie layer and try to read off SSDs. If it's still not there, if the ledger it knows it's located in cold storage, it can still go read it directly off that system as well. So you actually have access to all that data at all three layers with no additional changes to the architecture. So partitions versus segments, why should you care? I've talked about it. I've sort of mentioned some of the shortcomings with partitions within Kafka, and you can see that they're assigned to a brokers permanently. A single partition is stored entirely on a single node. Again, the data has to be co-located. The retention of that data within that particular partition of the topic is then limited to the storage size of that particular node. If you have a 4 terabyte disk on your broker and that's serving that node and that guy takes it all up, then that's it. You can't have more than 4 terabytes of data on that partition. And then obviously 4 terabytes times the number of partitions, let's just say 3, but again, it's replicated. So you really can store about 4 terabytes. That's typically your upper bound on that sort of storage for a topic. Any sort of failure or recovery or capacity expansion requires rebalancing I talked about earlier, where you add an additional node, assign an additional partition, and the data is then reshuffled across it in order to alleviate the storage restraint on the first node that caused the issue. And then the rebalancing has a big impact over the system and affects regular traffic because the data is quickly shuffling. Basically, all the topics are inaccessible for reading or writing during that time because the data is in a large, you're basically copying 4 terabytes of data across 3 different systems, and you've lost track of it, so you have to stop the world to do so. You don't have to do that with Apache Pulsar. So sort of to visualize that, right, your logical view on the legacy systems, there on the left is a single partition. Every copy of that partition has to be co-located with those brokers, as you can see on the left, and stored on that disk. The same physical logical partition concept of a partition within Pulsar is then further broken down in segments, like we said. The segments are stored across as many bookies as you need, and the stateless brokers can go and access any one of these and read the data directly back. This decoupling of the storage from the processing allows us to expand infinitely easily up and down without any sort of performance penalty or redistribution impact. So let's look at some of the ways that, now that we've put the data in, some of the consumption patterns, the way that we get data out of Apache Pulsar. And I mentioned earlier it's both a unified streaming and queuing processes, and this is something that a current messaging legacy systems such as Kafka does not support queuing. They typically support this messaging model here known as streaming, where you have a single consumer reading off the topic at a time, and that way you ensure that the ordering of the messages stay the same. So in this particular case, we have 2 producers writing messages there, M0 through 4, writing into the Pulsar topic. Consumer number 1 is reading that particular topic, and he's getting the messages in the order that they were published. That's referred to as the streaming messaging model. I guaranteed I get the orders in the event that they were published. We also support a failover subscription. So if you have any particular one, you can have a standby one. If one fails, you can immediately transition over to the other one. So in this case of the failure of consumer 1, for example, who was the exclusive consumer in this scenario, and he dies, then then consumer 2 takes over the work and resumes exactly where he left off. with that subscription, he keeps track of the last messages consumed, and he continues processing. Now let's look at the queuing model, which is different. Again, something that's not supported. They simulate it a little bit in Kafka, but they don't really have true queuing in the sense that you can have, an infinite number of consumers coming in reading these messages. So again, in this scenario, you have the two producers on the left writing the messages, and you have what's called a shared subscription in Pulsar, which allows n number of consumers come in and get their fair share of the messages. It's equally distributed across the consumers. So this is more of your traditional work queue scenario where the data, you can have, if the topic starts backing up and you want to scale up the number of consumers, you can have 5, you can have 10, you can have 100, as many as you want. They will each take round robin, grabbing messages and processing them in real time. Let's talk a little bit about geo-replication and durability, high availability of the system as well. So in a disaster recovery scenario, you can have multiple Pulsar topics set up in different data centers. So rather than have a separate process like MirrorMaker or something else that has to do this processing and pull it behind the scenes within Pulsar, you can set up subscriptions within the namespaces I talked about earlier to be geo-replicated automatically. This means that when the message is produced and consumed in data center A, for example, it will be, and you set up the geo-replication, it will automatically be replicated to data centers B and C asynchronously behind the scenes without any sort of intervention on your part other than the initial configuration. And all the consumers on the other side immediately have access to that same message. This allows you to just have the multiple data centers come up and not worry about, business continuity coming in, and then you just reroute the producers to the new data center, and the data that they publish will be available there for you. This is automatically integrated with the broker message flow. Again, it's a simple configuration to add and remove regions. Basically, you specify the brokers, you specify one endpoint where the brokers are listening, and it can automatically work. And then it's done asynchronously is the default. And you can also, if you want to ensure no data loss and you want synchronous replication, there's also a way to do that, which I'll cover here shortly. But the traditional default asynchronous replication data center is basically set up like this. There's two independent clusters, the primary and standby. You configure identical namespaces and tenants in each because it's meant to be just a failover cluster. The data is published from the consumers to the primary data center there on the left, and it is asynchronously replicated there one way across the data center two. And then the producers, now let's say data center 1 goes down, you just start up the producers on data center 2 who are in standby mode, and they resume exactly where the last ones took off. So there's no sort of latency around setting up or getting the data set over there or processing anything of that nature. It's primarily designed to be a backup secondary disaster recovery scenario. Now, if you want to have a synchronous replication, then you really want to make sure that the data is available at all times rather than have an asynchronous call, and there's the potential for some data loss in that scenario where there's between the time that the message was sent and the data center went down, that there's a possibility of some data loss there. In this particular case, you basically implement what's known as a stretched Pulsar cluster using a single zookeeper instance, and you also use what's called as the broker awareness concept, and letting them know that you have to get an acknowledgement from a broker data center 2. But when you do the three-way commit that we talked about earlier, you ensure that one of those bookies is in the data center 2. That way, in the event of a data center failure, you're still guaranteed that you have one copy of that data physically in a different data center. And there's a bit of additional latency for this, but there's absolutely no guarantee. There's guaranteed no data loss. If you've acknowledged the message from the producer, it's been synced in both data centers and you have a copy, and you cannot lose that data. You can also set up the concept of replicated subscriptions. So not only do you just worry about physically keeping the data and moving it from point A to point B, and as far as data centers go, data center 1 to 2, you also keep track of where the consumption was on the subscribers. So these individual processing of those messages there at the bottom indicate the markers of where you checkpoint and say, I have consumed these particular messages, and this is the last one I left off at any point in time. Then in the failover scenario, you spin up data center number 2, your producers still have to go back and they assign to that same shared replicated subscription. They have the markers indicating where they last left off. So you don't reprocess the same messages twice. You don't skip messages and not process them. This guarantees that you resume processing exactly where the last point you left off, which is critical for some scenarios where you want to process every single data at least once. It supports a very simple programming API. So now that we've put the data in the system, let's talk about how to get the data out, do something interesting with it. We support all these major processing programming languages right now: C++, Java, Python, Go, and C. I've seen some other open source ones in .NET land. I've seen some come up in Ruby now lately as well. So the community is growing and adding their own. But these are the ones officially supported by the Apache Pulsar project at the moment. So let's look at a very simple scenario for get data in. Again, the Pulsar client creation couldn't be simpler. You basically point it to the broker URL. You create a broker based on that client, say, now this is the specific topic I want to write to. And then you just start writing messages. Underneath the cover, retries are handled automatically for you. So you don't have to catch any sort of networking exception within your code itself. The send API right there handles all that for you and just sends the messages. You can also, that's the synchronous version. So there, if you call the send method, it will block and wait until you get acknowledgement back from the broker that the message was acknowledged and persisted to disk. There's also the potential to do an asynchronous one where you can fire it, forget it, and maybe it gets persistent and maybe it doesn't. But then when you can also check to make sure that if it was persistent, you get a result back and you can act on it. You can also say, if it failed, you can roll back messages as well, but you can do it asynchronously for higher throughput. On the consumer side, it's the client, again, creation is exactly the same. You specify the broker, there you go. You're connected. A consumer, you say, I want to read from this topic, and you also have to provide a secondary parameter called the subscription name, which we alluded to a little bit earlier. Again, that's a logical construct within Pulsar that basically keeps track of where, quote unquote, you are in that messaging process. So if the consumer were to die and reconnect on that subscription, it will pick up directly where the last consumer left off. So it will survive JVM crashes, etc. You could spin up the next day, whatever. That metadata is kept in Zookeeper and then written to Bookkeeper as well, those offsets, so that you will always have exactly where you were in the processing. And then you just basically have your processing while loop. While you continue to receive messages, that's a blocking receive until you get the message. And when you get it, you can just process it and do whatever you want. And when you're done, you have to explicitly acknowledge the message to say, hey, I have received this message, I'm done processing it. You can also negatively acknowledgement, say, hey, I got this message, but something went wrong on my end, and this should get redelivered again, maybe to a different consumer. So there's a concept of a negative acknowledgement, or in that case, it's called fail. And then there's also the concept of a message timeout, where if you do not acknowledge it within a certain amount of time, Pulsar assumes that you died, the process died without acknowledging it, and it should be redelivered as well. So we make sure, again, as far as keeping, limiting messaging loss, we also do it on the consumer side. It's not enough just to persist the data, store the data, and keep it. It's also to make sure that the consumers actually receive and process every individual message and don't lose track of any single one. And that mechanism's built in there as well. There's also the concept of a schema registry, which I'll just touch on briefly. It provides type safety of applications on Pulsar. So underneath the covers, everything is just set as bytes. And so if you're a producer and a consumer, you obviously want to serialize those bytes back into something more useful. And the schema registry is how you specify or determine what those bytes in the topic actually should be turned back into. There's basically two types of enforcement on that. So if a client tries to write the data in there, you can block them and say, no, you must write, serialized object like a string, for example, or a particular JSON object or Avro schema. It must conform to that. And on the server side, it would also reject those messages as well from a producer or a consumer, and that way they stay in sync. So you can allow that to upload a schema on a per topic basis, and it communicates the information to all the consumers. They can come in and say, what's the schema, get the schema, and then start processing the messages as well. So again, at a high level, a Pulsar schema consists of just the name, what's the schema, the payload itself, the binary representation of it, whether and the type of language it's defined in. Currently we support JSON, Protobuf, and Avro. And it has additional user-defined properties. So you can say things like, this is for dev only, this was effective on such and such a day. So you can also interrogate the schema itself and determine if it's useful for your particular use case or if you're using an older version, etc. So talking a little bit about schema versioning and schema evolution. The schemas can change over time, obviously, and there's the concept of forward and backwards compatibility. Mention that when you add a new schema for a type, it becomes the next new version. And so these are some of the different scenarios where if you try to publish something with a new scenario, what happens? If there's no schema, that becomes version number, version 1. If the schema already exists, then it tries to use that same schema. If not, it might throw an exception, or it would say if it's determined if it's compatible and allow you to use that schema or not. So it's basically some sort of type safety. In a distributed messaging system, it's basically the only way we have to make sure that the data looks like what it's supposed to look like for both the producer perspective and consumer perspective. Now let's talk a little bit about my sort of favorite part of Pulsar, which is Pulsar Functions. So typically, going back a little bit, prefacing the scenario, why we need Pulsar Functions, right? When you're processing data modeling as streamed, or event processing, you consume the data as it's produced, right? A pub-sub scenario. I get the data, I process the data. What you want to do is, there's two different types of processing on that data. The lightweight compute, which is basically simplistic, stateless transformations and reacting to the data as it arrives, right? You take a single event, and that's all the information you need to sort of do the calculations, again, like a transformation. Then there's the concept of heavyweight compute, continuous data processing. I need to process a set of data, potentially merge it with multiple streams, and then do some additional processing once I've consumed multiple versions of that data, buffered up some data, calculating an average, for example, that sort of thing, reacting to it, doing some sort of machine learning modeling on that. And then the fourth type of processing is interactive querying of stored streams as well, which I talked about using Pulsar SQL. Traditional real-time processing had two separate systems for that. You'd have a messaging system that would store and just do the pub sub, and then you'd have an adapter, a compute layer that would have an adapter to the messaging system that could consume the messages and then do the processing on it. So for example, things like Apache Spark streaming uses the sort of model they connect to the messaging system and source the data. A Storm, Heron, more later, distributed processing framework. Some of the things like the case streams and other things also have a separate compute layer to access the messaging layer and read it that way. The problem with some of these traditional real-time systems is they have really powerful APIs, but they're complicated. And things like, for Spark streaming, for example, requires developers to use functional programming just to get basic functionality done. It's a bit of a burden nightmare to configure and scale and manage a separate system or two separate systems. And it's really not applicable for things like edge devices and other resource constraint environments as well. So it has some sort of drawbacks as well. There's a lot of advantages to it, and definitely not bad mouthing it, but there's some of the drawbacks to using a traditional real-time system. But what we noticed in my experience from doing a lot of distributed real-time processing and event processing over my career in big data at Hortonworks and now then at Streamlio and Splunk, is that a lot of the processing, the majority of the processing you need to do on this event data is very simple. Data transformations, data classification, some enrichment, some content-based routing, maybe extracting the data and loading some data, doing map lookups, doing some real-time aggregations, and again, very simple microservices sort of processing. A significant bulk of the work are exceedingly simple, and so you don't really want to have that processing overhead of all the complex system and functional programming just to do something like data routing. That just seems to be a bit much. And so if you look at the lightweight compute model, it's basically something like this: income messages, you do a simple function on it, and you generate one or more output messages based on that. That's your basic flow for those sort of simple, lightweight computing, data transformations, data routing sort of processing. There's also an emergence of a similar analogous thing of what we call serverless, and there's a lot of similarity to that. Pulsar Functions are what we would consider serverless. They provide a simple functional API. You submit the function just to the system, and it gets run whenever your event shows up. You can compose multiple of these functions into, in order to do more complex things. And obviously, they're very, very popular and continue to be popular. One of the most common one is AWS Lambdas, for example. That's a very common serverless technology. So where's the overlap in serverless versus streaming, right? There's a lot of overlap. We tend to solve some similar problems with both of these technologies, right? So both are event-driven. Both can be used and are used for analytics and data serving, and have compositional APIs. They can be configured, based for serverless, and some DSL based for streaming. Serverless typically does not guarantee message ordering, and serverless is typically pay per action. If somebody Lambda executions, per million, you get charged so many dollars for that. That's typically how they get metered and charged. Instead, so Pulsar Functions is your stream native computing using function, right? You can use the simplest possible API to expose the broadest audience of developers. You want this to be simple to write. Anybody, computer science 101 person can write these sort of things. You want to provide support for multiple languages, which we do. So Python, Java, Go, we all support Pulsar Functions for that. You can also use a native API for each language. That allows you to scale up to developers, so you can have multiple developers writing these simple functions. And you have the native message bus native concepts, right? Input and outputs are topics. So people are familiar with that very basic processing model and are very, very comfortable with their programming language of choice, can become quickly productive using these serverless functions, these stream native Pulsar functions. Also, we also support a flexible runtime, so you don't have to submit them up to AWS Cloud. You can have everything from standalone simple applications to distributed managing systems applications across multiple worker nodes and function nodes and Kubernetes pods and things of that nature. Really no limitation of where you run these things as well. So if you want to have a simple standalone application, for example, all with the functions running on your co-located with your broker, you have to do that. You're not required to have a Kubernetes cluster. You're not required to submit them to AWS, a cloud provider. You can have a self-contained broker doing all the processing as well. So let's look at the SDK-less API. We support an SDK version of Pulsar Functions as well as the one that does not require the SDK. This is the Java version of that. So I apologize to the Python developers in the crowd. But basically you use the existing the Java function API, and you have a class that implements that, and you specify the input and output type. And then all you have to simply do is override that single method, which is provided in the function API called the Java function specification, and you just take the data and return it. That's it. So every time an event gets called, your code gets executed and you perform that function. Obviously, this is a very simplistic Hello World version, but the point here is that you can basically do this in 3 lines of code and a little bit of scaffolding around that. Nothing really complicated. So the friction to getting started is next to nothing. We also provided a more complex SDK version as well, which requires you to import and use the Pulsar Functions API jar, and then you implement a different interface, Pulsar function. The big difference here is that the method name is now called process, and in addition to getting the input data string as you did in the previous one, you're also provided a context object as well, which provides hooks back into the processing framework, which allows you to do logging, get access to configuration variables, record metrics, get metrics, store state, things of that nature. But again, it's a very, very slight deviation as well, which you get a lot for. So that's the SDK API there. So let's get into some of the semantics here. So the function is executed, again, as I mentioned, on every message that gets in the topics individually. You can also have multiple input topics. So you can use like a regex and scan multiple topics. like for all inbound emails, etc. All the output, the function output automatically goes to an output topic as well. So that's kind of, I didn't mention that earlier, but all this wiring up and trying to create a consumer or producer and, create the subscription, all that sort of stuff is handled for you automatically under the cover. That even that code is handled for you. And then whatever you return from that function, quote unquote, returns function automatically gets published to the output topic. You can also do void as well. You can just simply process the function. Your function could do something like update a database table and you want to return null, just to return void, just to indicate that you're done processing it. And then the built-in serialization takes care of from the schema register we talked about earlier, automatically handles the serialization, deserialization of the messages. So rather than doing just a string and you have a more complex JSON type, and your function takes that as an input type, it will automatically, it will deserialize that object and create one for you, so you have an actual instance of that in your function. You don't have to do any sort of call to a serialization library or deserialization to first get the data and translate it from bytes. That's happening for you automatically. So then Pulsar functions, you can also request certain processing guarantees, which is also true in general across all Pulsar, but you can say at most once. So the messages act as soon as you get the message, whether you process it or not, you acknowledge it. Whether you succeed or fail, that's sort of the scenario. You can say at least once, so it's act on a successful completion. This is the default behavior bit built in, so we have auto act built into a message, so you don't, as you may have saw earlier, or recall earlier from the client code, there where we explicitly had a consumer and we got the message, and then we explicitly did an acknowledgement on it. Here we had a concept called auto acting, and so it will automatically act the message, and you don't need to add an act call inside your function as well. So again, we keep it clean. You're really not aware of the API underneath the covers. You can focus exactly on what you want to do with the code within that logic block. And then you can also specify that I want effectively once, using its effectively once semantics to keep track of message deduplication, idempotent processors as well, and that you guarantee that you process that message exactly once. And this is controlled. You can configure that at runtime by the user. So when you deploy it, you can specify, I want this particular processing guarantee on those messages. They also have the concept, at least the SDK enabled one, have the state management built in as well. So you can store state between calls as well. So you not only have to have stateless functions, which do a transform on the data, you can do, again, things like aggregates and keep a running total of the last 50 values of a message, and then I react on only on the 50th one as well. That's built into the framework. The context has a state, put state, and get state methods, which are key value interface. You can store data, store an element, retrieve it, and then restore it again as well. The biggest advantage of this is, again, there's no secondary system you have to stand up just to do persistence of data. It's built in to the Pulsar Functions API framework automatically as part of Pulsar. So let's take a look at some of this, or examples using a stateful function. So this is a counter function. Very simple. You get in a string, you split it by the new line characters. This is basically your word count scenario. And then you increment that by one every one of those times. But then on every subsequent call, it'll continue to add and add and add. So if you wanted to calculate how many words are in a particular book, for example, and you published into that topic every the content of that, either line by line or page by page, this processor would count all of those, and then at the end you'd be able to access that individual value and give you a result. So it's actually distributed state, and it stores across time. So I talked a little bit about Pulsar function runtimes and the scenario where you'd want to just do, you could co-locate on your broker, but there are multiple options, right? Obviously, for a scalable system, you choose the one that's right for you. So the first one is you can co-locate these functions on the broker itself. And you can see here these little boxes at the top. There's word count function, transform functions, and those can get co-located and run as processes on the same node within the broker as well. And so there's no additional hardware required. And this is a useful scenario where you have a small number of very simple functions, and you don't want to stand up another system. You're just playing around with it in a dev environment. You only test one or two at a time. you don't need to set up an additional system. You can test it all here. It's fully supported. Deploy your functions to the broker. Broker executes them automatically. The downside is obviously this is not something for production because the processes on that broker are competing for resources with the broker. And in the event of one could cause the system to crash, which would have a cascading effect on that broker could crash, which would overload an additional broker, et cetera, et cetera. So you really want to isolate those guys. So there's two additional ways to isolate those functions to limit the potential for any sort of cascading failure resulting from a function failure or out of memory, that poorly written function that has a memory leak, et cetera. And the first one is that we have introduced the concept of worker nodes. And so you can dedicate a set of nodes within your cluster specifically for hosting and running those processes as those functions as processes on those nodes. So it's sort of like the first one, but it's rather than running them as processes on the same nodes as the broker, you just have dedicated machines for it. And then that gives you resource isolation, it insulates you from a failure scenario, but you do have to spin up additional nodes for that. And you have to maintain that as part of your infrastructure. Your DevOps teams has to be aware of those and spin those up as well. And then keep an eye on those and scale those if you need to increase the number of nodes to support your number of functions. And there's also the ability to, the preferred method is obviously Kubernetes deployment mode. So you can have those, each one gets spun up as an individual pod. So you can have multiple instances. They're running independently of one another. They get co-located on whatever resources available in the Kubernetes resource pool. They get spun up and so you don't know where they're going to get located as well. But this provides you all those different features there at the bottom, which is fault tolerance. Kubernetes by default, for example, if a pod dies, it tries to restart it automatically. Parallelism, that's supported in all cases, but this makes it easier because you just scale up more pods. So if I need, 5 different data routing functions, for example, because I see that the back pressure on that topic that is consuming is not keeping up with the data, I can just increase that function count to 2 or 3 or 4, and that will just spin up additional pods running that same function. Elasticity, so they can scale up and down. Load balancing, that gets distributed across the resource pool, across all your nodes evenly. And you have on-demand updates. So if you update the Docker image that is hosting that particular function, then when you basically restart it, it will go source that, it will pull up the new image, and you automatically get the runtime and get an updated version without any sort of downtime on the pod itself. So let's take a little bit about the Pulsar performance and how we do compared to some of the other messaging systems here. Hopefully you can see this. This was done independently using the open messaging benchmark, and it's a little bit old. We actually have newer, better results than this, but this membership indicates the publish rate of Apache Pulsar versus Kafka. Again, and then Kafka sync. So the Kafka one at the bottom, they're using synchronous, so we force them to write all 3 copies to disk first. And you can see the rates are under much lower. If you allow them to do asynchronous, they get some increased throughput, but across the board, Pulsar is just better. And again, I alluded to that earlier, the architectural structure was split in across 3 different bookies to write the data, using a separate journal to have a separate read path, and using an fsync and journaling mechanism is how that's achieved. That's the net result of all that architectural design that we did underneath, is to see results like this. You can consistently publish at a higher rate. And additionally, the performance latency, the tail latency, the P99 latency of all the messages, relatively compared again to Pulsar to Kafka is just much less. So overall, we just have a much lower latency, consistency latency. There's no big lag between the first message and the very, very last messages. It's very, very smooth. Message performance and consumption is there as well. So let's talk about some of the different, now that I've talked about before, let's just sort of summarize some of the different comparisons, us versus them. Again, durability, I've stressed that point quite a bit. Our data is replicated automatically and fsync to disk. Theirs is not. They have a backdoor mechanism that tries to keep it synced up, but there is a scenario where you can lose data. And there's a great blog post by Jack Van Lightly that shows you how to lose data and not lose data. He again, independent third party, interested in messages systems compared to us, Kafka, RabbitMQ as well. All of them put them through their paces, tried to force them to lose data, was unable to do so for us, who was able to do so for Kafka. Multi-tenancy is something that's supported natively in Pulsar. Kafka really didn't. If you had access to the cluster, you could theoretically read all the different topics of this. There's an additional layer of security built into the data access, which is a nice feature. Tiered storage is again something I talked about earlier. You can offload to colder storage for long-term retention, and that's happened automatically. There's no additional stop the world, spin up additional load, and load the data required to use data from tiered storage. Yes, you can do that in Kafka, but you have to. There's an additional mechanism to move that, offload the data back on S3 onto a broker that has the data on disk, because at the end of the day, Kafka reads the data directly from a local disk. So that with Pulsar, you can read it directly from tiered storage with no additional hardware required. Out of the box geo-replication as well. Again, we don't require an add-on or third-party vendor solution to do your geo-replication. That's open source and free. It handles it quite well. Asynchronously and synchronously are your options. Seamless cluster expansion, that's just a big pain point for Kafka. Again, you have to you can throw new nodes into their cluster, but they don't have any data to serve. You can't alleviate the pressure of a filled up topic without repartitioning it, and then that requires halting your cluster and reallocating the data across all those particular new partitions. With us, you just add a new broker to handle a stream layer, or you can add a new bookie that can handle load immediately. So your mean time, turnaround time is seconds, and there in Kafka it's minutes or worse. Pulsar Functions is just something we have the lightweight flexible compute on top built for you. They have additional frameworks that sit on the side, like KSQL, things of that nature, but they're a secondary system running up and sourcing the data. They really don't have the sort of functional programming serverless model. There's just no equivalent that I'm aware of in Kafka. Unified messaging model, we support both topic queuing, and so streaming and queuing. Again, that's something that they just don't support. A lot of customers from my previous company, Streamlio, that was their primary use case, was to unify their messaging systems. They often would have Kafka and RabbitMQ running side by side with basically twice the cost, administrative costs, et cetera. They're like, why are we doing this? They put up Pulsar in there, and they had immediately savings of 50% on hardware, and they were able to serve all their existing use cases quite easily. Higher throughput latency, like I showed in the previous slides. Again, independently messaged, benchmarked and tested. Feel free to run it independently. It's an open source test. Run it if you want, verify your results. And then highly scalable. It's been proven in production for millions of topics, which is again a pain point for Kafka. They can only have used to be much less. They've recently increased. They're very excited they can get up to 200,000 topics. That's great. We can do 1.8 million, 2.6 without any problem, which simplifies your programming model. The topics become basically cheap, and you can throw them away. So you can stand up a topic intermediate, throw it away. You don't have to worry about it too much. Makes data modeling much easier to have multiple buckets to store your data in without worrying about artificial constraint by the system. Growing ecosystem of systems that we integrate with. We have connectors and plugins for all these different popular systems. Everything, databases, Spark Streaming, again, S3, RabbitMQ, all these different systems, InfluxDB, Cassandra have done that. You can actually source the data from Elasticsearch, publish it to Elasticsearch, etc. You can pull data from Kafka, put it back on Kafka, whatever you want. All these different systems and growing. I'm leading that effort in Splunk. That's sort of my team is working on the connectors, and so some of these will eventually get open source as well. More in the pipeline, I can assure you. These are some examples of companies that are using Apache Pulsar. So no, it's not just a little toy project that people don't, have just play around with. There's actually people using it in production, using it open source, using it in production as well. A lot of people using it are interested in it for their use cases. They're also seeing limitations within the existing messaging solutions and are looking for alternatives, and have reached out to us. Those I would consider the open source evaluators. So like, hey, we're not happy with our current system. What do you have? And they're currently evaluating that as well. So it's a growing in popularity for sure. Also, all these companies have taken the big leap and moved it into production and are running their production systems on it as well. So you can see there's quite a bit of large companies, diverse companies. I can just mention there's quite a few in China, and if you look at the size of their clusters compared to some of the ones in America, it just puts ours to shame. Multi-thousand node clusters all day, in the traffic that they deal with is just just puts some of the other websites here in America to shame. They're really quite data intense, and they find that Pulsar is really the only thing that serves their purpose. So it came out of Yahoo, the birth story of Pulsar. Just sort of wrap it up here. Again, I appreciate your patience. It's been very quiet, so no questions, which is great. It basically came out of Yahoo. They needed to collect data and distribute it across for all their different internet scale. These are some of the core systems within Yahoo that it served, which was Flickr, Yahoo Finance, Yahoo Mail, Yahoo Sports, and Gemini, which is their key value pair system. Basically, they had a fully replicated 8 global data center cluster, over 100 billion messages a day, 2.3 million topics, fully geo-replicated without any issues. It's been that way for 5 years now. So it can definitely scale and handle the load and run everything that Yahoo needed it to do at internet scale. Right? These are all the different specifics of how big it was, your average latency, even across a big system. No data is lost, multiple applications, self-serve provisioning, everything here, all the different bullet points of just takeaway is it can run at very large scale, but it doesn't need to be. But you can scale up as large as you would possibly need it to be. Just finally wrap up of some of these. Okay, so we introduced the technology, some of the differentiators. Let's get into some of the example different use cases of what we've seen people do and people are continuing to use to do. Again, I alluded to it kind of in the first section, and we'll just cover it again or bring it back up. Real-time monitoring and notifications, interactive applications, particularly for mobile devices, log processing and analytics, which is a big one for us at Splunk. It's also used for IoT analytics. It's very lightweight. Again, that decoupled storage layer allows us to put a broker basically and an MQTT plugin for Pulsar on an edge device, on a resource-constrained device, and host Pulsar functions on the edge as well. So industrial IoT use cases can be easily implemented with Pulsar out of the box. Again, then your basic stream data transformation, real-time analytics, data distribution. So basically, content management. I got to replicate my data for streaming services across multiple locations or put it in the cache in different geolocations, and event-driven workflows. Some of the data-driven workflows are some of the basic flows of a data-driven workflow is that an application comes in, you need to do all these different processing steps along the way to get the data to a result, and each one of those little gears can be implemented as a Pulsar function. So you can have one to do the decryption, extract some different values, convert it into a normalized form, for example, dispatch it to another topic or queue, or get processed and eventually stored. So you can basically implement it with like 5 simple functions, and you can sort of interweave those all together or create a composition based on Pulsar functions for that. For data distribution, again, multiple different data sources. The data is collected, you normalize it, do enrichment transformation, you put it into topics, and then it's offered as like data as a service scenario. So if you're connecting analytics on a, one scenario we looked at was an energy actually trading platform. So energy producers will publish their resources for sale, and they'll do the analytics. So what's the market in real time? What's the price for this particular information? I get data off the grid, for example, and avail that out and make that available to people as a subscription, and they can subscribe to those services and get the data as it's processed in real time, not a week later, not a day later, but in real time. So like market data that you want to react on quickly is a very good use case for that. Again, data pipeline simplification, I sort of talked on that, where you have at the top, you have the traditional one where you have multiple systems, data coming into one location, a Spark connector, pulling it off, then you put it into a data lake, then you do analysis. Pulsar can do all of those things in one step. So you can replace, and like we've had customers replace a complicated system like this with lots of moving parts into a simple unified process, a data pipeline using Pulsar. Event sourcing, is something that really Pulsar really excels at, that no other solution in the market today. Some people are eager to get into that market and will make claims. Again, like Kafka will say, oh, you can do that with event sourcing. Just because our messaging system doesn't mean you're an event sourcer. Event sourcing basically means you keep the events from the beginning of time and forever. And then if you want to restore the system state, you replay the messages and reprocess them, and you restore the state to exactly how it was. So the example would be like a database scenario. Let's say event number 1 is create the table. Event number 2 is insert, update, etc. And you keep a million of those, and you want to restore that database table. You just keep all those records and you replay them from the beginning up to the latest one. And in theory, your database table should reflect exactly what it should be, as if it had been, updated separately using a system using traditional models. In order to support that, obviously you need the infinite retention, and Pulsar obviously is the only really one that supports that easily and seamlessly. And so you can do that sort of use cases are all handled by that. We can't disclose the name, but a large auto manufacturer here in the United States that uses it for their connected vehicle. Again, the scale of this and pulling the data from their sensors in their connected cars over a wireless cellular network into Pulsar for processing, cleansing, enrichment, and refinement. And then it's segmented out and sort of delivered to individual teams for do analysis, everything from marketing and to engineering, and they can detect faulty systems early. You might need an oil change. Hey, you're bringing your car for a particular service right away because we see your oxygen sensor is very high. It's above average for others, and that sort of thing. So you can have all that different information. They get it in real time. They can react to their customers much more quicker. Last one, I'll just talk a little bit about it. I believe here's the connected consumer. So you have consumers on their mobile phone, their electronic devices. The emit data is collected and processed, and then you can generate notifications of work requests, right? So my smart speaker doesn't work or stopped working. You don't have the customer doesn't have to go onto your website and report a case. They automatically know. For example, it's a big electronics manufacturer. Hey, we know your smart speaker went down. We're going to go ahead. We have to put it and send an alert to you guys, and we already know we're going to send you a replacement, or we're going to send you to create an appointment, schedule an appointment for some email that says, let's schedule an appointment at our next service center and get it fixed for you automatically. And so that's just another scenario that they do with that. Supports IoT environments as well. I sort of alluded to that. So you can have typical sensors. You can have that deployed on the device. You can have smart devices. Edge nodes is where the Pulsar broker can be co-located, and with that addition to the MQTT support, the lightweight protocol support, we can communicate with the smart devices and the light devices and collect that data and just start doing the complex computational logic and do some storage and aggregation there and do alerts right there, and then obviously load it up and put that information to the cloud as well. So it's really also supports IoT environments. Sort of a high-level IoT data fabric is also something that you can do with Apache Pulsar that you cannot do with Apache Kafka or any other really distributed messaging system. There are nice messaging systems geared towards IoT, but they do not have the end-to-end storage. You cannot get it from the edge all the way into the cloud and back again. I think that's one differentiator as well. So you have different Pulsar edge devices deployed on IoT gateways, sort of level devices, or basically glorified Apache or Raspberry Pis out there. You can deploy the functions out there. And then the smart devices there indicated with these communicate over WebSocket or MQTT, and we can get those events and do processing real-time analytics on that. I did a whole talk on that. It's available online about doing real-time IoT analytics on the edge. If you want to learn more about that, go Google for that. It should be, my presentation should come up pretty quickly. Maybe even a recording of that talk if you want to delve more into that particular use case. But again, that's something that you can do as well. So if you want to do analytics on IoT data, you can do it real time with Pulsar. So a few more readings as well. Again, that's the Jack Van Lightly blog I alluded to earlier about how it works, and he did some testings, how not to lose messages on there as well. It's a good read. Again, independent. He didn't work for us, never worked for us. He just sort of, guy's really interested in messaging and wanted to run all the messaging systems through their paces and have blogs about his various experiences with each one as well. Some of the Streamlio blogs, which have been moved, and I apologize for this out-of-date link. Since our acquisition by Splunk, they have been moved to the Splunk blogs, and so you have to go over there and search for Pulsar, and they will come up quite easily, but they're not readily available, and they're no longer at these sites, so I apologize for this out-of-date links. Having said that, it's been very quiet. Are there any questions?
Yep, I will start, okay? Once again, if you have any questions, please use the button, the raise a hand, or write on the chat. We'll unmute you. The first one is a question from me about the exactly one, and you call it the effectively one.
Yes.
So yeah, I'm actively using the Apache Kafka, so I the deep in the knowledge about how it works, and I know that exactly one is like the it depends where and which product and which company it's called. Yeah, we have this holy grail, and we have exactly one. But what is the reason behind you don't use the name? I mean, you change it to effectively one.
Well, yeah, because we don't want to over promise what we do. We want to actually, our concept is be truthful, because people will find out pretty quickly. We are not to do exactly once requires some additional framework and work that is in the pipeline that is not currently in the Apache Pulsar product, primarily and specifically the support for transactions and the use of a third-party event so that you can keep track of exactly where you were. So remember when I was talking about the replicated subscription, there is the scenario where you could process a batch of messages and have it fail. And if for whatever reason the acknowledgement did not get, so on the acknowledgement back, it got lost and it could get redelivered, right? And so that scenario without a transaction case, then you would basically reprocess that message. And so you'd end up duplicating processing the messages. That's the real gap that's there right now. So there is a way to simulate it, but that would basically require you change it and you use the reader interface. So there's two APIs, the consumer, which is just, it automatically manages where that pointer, that offset is for you. The reader one allows you to specify specifically. And so in order to do exactly once with Pulsar, you would have to use the reader interface and have a third, right now, an external system like a database or a cache or something that you trust, and persist that data there. So every time you quote unquote acknowledge the message, you actually update your pointer in your third party persistent system. That way, if you ever go offline, you come back up, you first come in, you acknowledge it, access that system again and say, where was I really? And so even though Pulsar thinks you may not have got that message and tries to deliver it to you again, you can say, no, I don't want that one. You can skip right ahead to the one that you are interested in. That's really the only way you can do exactly once with Pulsar right now. But once we get transactions in place, which is a current PIP, Pulsar Improvement Process, and it's underway, there's a lot of work under that, but it's not there yet. So I don't want to say it until it's there.
Okay. And the second question is that I see a lot of components in the Pulsar ecosystem, I would say. There is a Zookeeper, you have the nodes and all the stuff. So is it not too much? I mean, most of people believe in the rule that keep it simple, stupid. Example, the Kafka, it's trying to get out completely from Zookeeper. And what do you think about it?
Yeah, I mean, I support their effort. Obviously, simplification is better, but simplification so you should really reduce a problem to its simplest components, but no further, right? There's also, that's the opposite of the keep it simple. And oversimplification is sometimes a problem. And so Zookeeper supports a very important function, particularly within Pulsar. And it would be, we have talked about potentially rewriting it, but we would basically internalize what Zookeeper does now. Because at the end of the day, you need a distributed state management store. And so whether you use an existing stable one that's been out in the public and it's evolving on its own for 10 years, or choose to rewrite it yourself, is really your own choice, but you have to implement the consensus algorithm and deal with all these conflicts and that sort of thing internally. So we prefer to keep it, the leverage, we're not experts in the distributed, well, I kind of take that back. We have one guy who commits to Apache Zookeeper on the team, but we're not as a whole or distributed consensus experts. We prefer to use that system that does it well for that. And I think there's a lot of benefits for that. The overhead of that within a Kubernetes systems now that it's been automated, it's been minimized. The biggest concern used to be, hey, I got to stand up and manage this whole other system. Now that you basically specify it in a Helm chart and it spins it up for you and it's another pod in your stack, I would say it's less of a problem. And so it's more of a purism versus not sort of argument at this point, because it's really simplified at this point.
Okay, thank you. Next question is about the cloud, because many organization is already using it. So do you have like dedicated cloud? I mean, example, the Kafka have the Confluent cloud or something like that. So if you deploy your environment in one of the cloud provider, you don't need to create your own instances and install it the Pulsar. They just give you the endpoint of their cloud, and the traffic is inside of the cloud provider.
Yep. So at Streamlio, we offered a managed service that did that, but obviously since we were acquired, that shut down. But in our stead, one of our previous co-founders has started a company called Streamnative that offers that service. I'm also aware of two other ones. Kafkaesque is another one that offers it as a managed service. And I recently have just started seeing advertisements when I Google for Pulsar coming up as well. So there appears to be a growing number of managed Pulsar as a service providers, at least 3 that I'm aware of out there that offer that exact type of service. And so you can contact them and get pricing and pilots and so on. But yeah, that's definitely an option now in the market for sure.
Okay.
So I do have a question as well. So first will be, how does Apache Pulsar rely on Zookeeper? Can you elaborate maybe which metadata and how heavily does it rely on Zookeeper, and exactly which which data are there?
Yep, that's a great subject. So I'm covering that in my book in greater detail. So the impact is very light. Let me just put it that way. It is used primarily, again, so when we talked about the segmented architecture and the ledgers and the individual segments, that Zookeeper is used to store that metadata information. So if I want to know what a topic is, inside of Zookeeper, I keep track of just a list of all the ledgers or the segments that constitute that particular topic inside of Zookeeper. That's what it's used for. And also keeps track of which broker is serving which topic. But since you only roll over a segment every 50,000 messages, it's basically accessed once every 50,000 messages from a performance perspective, if that makes sense. So out of every 50,000 messages that are either produced or consumed, Zookeeper is called exactly once inside of Pulsar.
Okay. Second question will be about consumer API. On your presentation, there was visible that consumer implementation or consumer usage in our custom implementation acknowledges that they end the processing of this some messages from queue. Are there acknowledgement messages put in batches somehow and then sent to broker, or each acknowledgement is sent to broker straight after invoking acknowledgement?
So you can configure them to do both. It really is up to you. If you want the granularity of every individual message gets ACKed, and so the redeliver cycle is usually about 1 minute, and so it's not a hard block on a queue. So let's just say you have a topic with 1,000 messages and 3 consumers. Third consumer is misbehaving and he's not acknowledging the messages. Those messages 3 and 6 and 9 and 12, etc., will get they'll basically either be timed out or negatively acknowledged. They'll get redelivered within 1 minute. And so it could be a batch or it could be individual, but it doesn't matter because the redelivery of those messages is buffered a little bit. It's delayed. But if you're an exclusive consumer, then they get delayed for you. In that scenario, on an exclusive subscription, then that same message is retried. But in a shared subscription, they get sort of knocked back a little bit back further in the queue and get redelivered at a later time because you've already agreed or basically conceded that message order does not matter to you as much. That makes sense.
Okay. Thanks, sorry, Konrad, because let's give a chance to the next one. And Mishek, your turn.
Okay, sorry I wasn't on from the beginning, and this is my first contact with the Pulsar. I've got, let's say, the use case something like for the IoT. So my question is, let's say I have a device that produces messages, is actually a producer and is, let's say, able to connect every only 1 hour for 24 hours. Let's say it can be synchronized only in a specific period of time. Is it possible that the messages will be just queued on the device and then sent to the Pulsar? And if so, where does the device keep these messages, in memory or some local disk storage, so on?
So the scenario is you have a smart device that is going to store and you want to store and forward messages to Pulsar at some point.
Yeah.
Correct? Yeah, that's really going to be dependent on that device's capability to store and buffer those messages based on its hardware. That's really an outside of Pulsar concern. What I can say that people have in some of those scenarios have had to do aggregations on those devices. Sometimes they just have to accept the fact that it's not there. But typically, in an industrial setting, for example, the IoT gateway is within the device, so it's constantly within radio contact within range, short range, MQTT range of communication, so it can continuously send the messages. But it sounds like in your scenario, so your device physically, consciously turns itself off, or it'll wake up once every 24 hours. Is that correct?
Yeah. Yeah, the example is that for, let's say, with those cars, and let's say that because you said that you were talking with the company that was doing stuff with the cars, and let's assume that those cars are 24/7 connected to the internet. That's easy to do. But what if those cars are, let's say, going to the major main base and only then they have access to the internet?
Right. Okay.
So
That's
have buffered those messages.
Yep. Okay. Yeah. Great. I've seen that. Also, would like for the insurance companies did a similar thing. Like, hey, if you want to save money on your car insurance, let us watch how you drive, sort of scenario. And there's no guarantee that you're connected at any point in time. So they would actually have obviously try to store what they can on those physical devices, but there's obviously limitations on the memory that you can put inside of a passenger car. And so they would try to create a customer to opt into a secondary buffer. And one of those would be like a smart fob, plug this into your car and allow us to download that data, or a smart app on their phone, and it would actually store the data on their phone, which has much more storage. And then when they would connect back online, it would actually connect over the cellular network and send the data back home.
Yeah. Okay.
But basically you have to, at some point you have to add the physical storage. And those were two ways that I saw them solve that and store that data. They just have to buffer it. But if worst case, old data falls off, right? And so it's just one of those make your buffer bigger sort of solutions with hardware.
So anyone did that already?
Yeah, that's exactly how they do it. So one of the major auto insurance companies, that's exactly how they do it. You download an app on your phone, it will connect. You have a telemetry device like a fob you plug into your USB connection on your car, and then it'll collect the data, all your telemetry data, and how you're swerving and driving, and all your motion while you're driving, and then it stores it on that thumb drive level thing first. If that overflows, it'll try to connect to your mobile phone and buffer the data there. And then when first it tries to send it off as fast as it can, but whatever it has to buffer, it buffers, and then when it finally gets back online, it can send it off. And so typically these outages are short, like you drive through a tunnel, you have other sort of things. For this particular scenario, because you're always driving. right? And so and then you're out for a while, you get back to your house, and then your smartphone connects to the internet because you jump on your Wi-Fi, and then that Wi-Fi says, oh, I got some data, and it sends it back home. So usually they were pretty happy with the amount of data they got. There was always gaps, and it always came back to how do we add buffer to these devices to get the data stored during these outages where we're off the network, out of the cellular network range.
Okay, thanks.
Yep.
Okay, who's next? Konrad, maybe you?
Yes. Okay, David, can you give me some advice if I should be particularly careful about the bookkeeper layer in Apache Pulsar deployment with, let's say, high load system? Because it seems that the bookkeepers do a lot of f-syncing while they are working with Pulsar, and I'm just wondering if we should be particularly careful about them while having processing, let's say, tens of millions messages in short time.
So was it Zookeeper or Bookkeeper? I'm sorry.
Bookkeeper.
Bookkeeper. I would say, so you're worried about the ability to handle the throughput of like building of a very bursty sort of workload, and would there be any sort of disk issue? We've not foreseen, again, we've done it at a very large scale, hundreds of billions of events per day, and we've seen peak usages of, we're currently working for a customer, we're able to do 3 petabytes a day on our way to 6. So the real issue is, obviously, you're always out, is to scale out the cluster. Scale out bookies, you can just add them, which obviously adds then a new device path, which obviously gets you then roughly 6 megabits per second on a typical SSD of write throughput. So that's typically the metric we use to say, okay, what's going to be my max megabytes or data volume per second, and then divide by 6 megabits per second because that the bottleneck becomes your disk driver, and then just make sure I have that many instances, really.
Okay,
that way
so
you're guaranteed
that's
that.
only a matter of calculation, as I see.
Yeah, if you're absolutely concerned about it, again, there's built-in back pressure, right? So if you try to write to Bookkeeper and the disk your f-sync is blocked because you're writing the last couple of messages, it'll buffer up and back pressure, but you'll have latency on the system, right? Because you're waiting for the next f-sync to complete. You get in the queue, so you have to alleviate that queue pressure by scaling out your number of f-sync your devices, basically. Yeah, but look, if you really want to drill down, the way we're doing the performance is to monitor that queue depth on the storage device drivers, and if that gets too high, then you have to automatically add a new bookie, and we're kind of looking at doing that automatically with some of our Kubernetes magic around auto scaling. We sort of use that as a metric, and if it gets too high consistently, we trigger it, and just add a new one to the cluster. Is what we're actually doing for the 3 petabyte a day performance.
Yeah. So let's give a chance for Michał. By the way, Michał is our presenter. His presentation about graph databases and Neo4j was one of the best one, I would say, in the most participants. Michał.
Okay, hi, thanks for the introduction. I was offline for a moment, so sorry if somebody has already asked this question. Anyway, you mentioned quite many companies that already use Apache Pulsar, but I wonder how many of them actually used Kafka in the past and decided to migrate to Pulsar? And if so, according to your experience, how difficult, how troublesome this process is? Because if I understand correctly, the differences between Kafka and Pulsar are so big that this process for sure is not transparent and requires some smaller or bigger effort.
Yeah, great question. So I have an exact number. I can say that I know that the vast majority of them had existing Kafka systems, and whether the Pulsar that they added was a direct replacement or an individual project sort of own messaging queue to avoid getting into the Kafka mess because they've spoken to their peers and decided, I don't want any of that Kafka nonsense that's painful for these people. I can't speak to whether it was complete takeout. There is one blog post where a Chinese company specifically walks through the process of why they chose to replace both Kafka and RabbitMQ and unify it on a single Pulsar cluster. And that one is available. Zhaopen is the name of it, Z-A-P-H-I-O-N, I believe. Feel free to Google that. There's probably, they did a presentation. They also did a blog post on it quite well. As far as friction of migration, that really isn't an issue because the API is quite similar. It's a pub sub mechanism, so porting over the code. There's also connectors to pull data out of Pulsar or out of Kafka, put it into Pulsar. There's also, so you can sort of migrate your data quite easily. And then the programming API is very similar as long as you use stock of Kafka, right? Put and get, or, publish and, subscribe sort of semantics. When you start using their third-party tools, and obviously the effort grows exponentially. For example, replacing KSQL with the Pulsar SQL stuff is a whole another issue unto itself. So if you, I guess there's no really single answer, but that's sort of some of the tools that are there. We also support Kafka on Pulsar as another bridge technology over that recently came out by another a contribution by another company that decided that they wanted to get off, but they couldn't get off right away. So they decided, well, let's figure out a way to first stand up Pulsar stack, and then we will run Kafka on top of it, and then eventually we'll just pull Kafka away, and then nobody will know the difference. And so they actually also implemented that as well as a bridge to move over from one to the other.
Okay, I think it is enough from my perspective.
Okay. Yep. Great question. Thank you.
Cool. Okay. So last chance. Any questions? Raise a hand or let us know. I think, yeah. Thanks for the great presentations. Yeah, I'm using Kafka every single day, but yeah, I was really interested how it's like some Pulsar, and I think I got all the questions, and all the answers. That difference between, and it's Pulsar looks really promising. So once again, thanks for accepting our invitation, and thanks for the great presentation.
No problem. Thank you. And I just want to leave with you some additional resources. The Apache website, obviously, the Slack channel is very active as well. Just jump in, ask your questions. Shameless plug of my book if you want it. And also GitHub repo, some examples of using Pulsar functions in greater detail. It's open source code. Feel free to play around and have some detailed examples. Everything's there. It's free and open, and enjoy.
Yeah. Thank you.
Thank you very much. Have a great day.